Further Algebra, Lesson 6, Partial Fraction Decomposition. So, before we introduce the concept of partial fraction decomposition, let's look at a very simple case scenario. Supposing I ask you to simplify this algebraic fraction calculation. You've got to carry out 1 over x minus 3 subtract 2 over 2x minus 1. Simple. We've done quite a lot of practice on this. You would potentially say you're going to cross multiply like this, which would give you 2x minus 1, subtract 2 bracket x minus 3, and this would all be over your lowest common denominator of x minus 3 and 2x minus 1. You would then simplify your numerator, which gives you an answer of 5 over x minus 3, 2x minus 1. Very typical, very simple piece of algebra. Now, let's change the question completely. Let's say, what if you were given the result, the end result, 5 over x minus 3, 2x minus 1. So you haven't seen any of this working here. You're just given this as an algebraic expression. Let's suppose you're now asked which pair of fractions were combined to create this as an answer. Now, that's a much more complex question. It's very easy to add or subtract a pair of fractions together, even a pair of algebraic fractions, but it's much more complex to go the other way around. A similar example, numerically, what if I said, here's the answer, 3/4? Well, what's the question? Which pair of fractions could combine to give me an answer of 3/4? Well, it could be a half plus a quarter. That would be a correct option. But 3/4 could also be made up of 1 take away a quarter. And there are many other, infinitely many examples that we could put together as well. So is that the same for an algebraic example? That's what we want to find out. Is it possible to work backwards? So having been given a single fraction like this, is it possible to work out which pair of original fractions would have perhaps been added together or subtracted to give us this as an answer? And that's what we're aiming to work towards. So as ever, we'll start with an example. We're going to consider the algebraic fraction 2 plus x over x plus 3, 4 minus x. And we are going to try and find out what fractions originally combined to create this as an answer. So let's go about this logically. Now we know to create a common denominator of x plus 3, 4 minus x, one of our fractions will have had a denominator of x plus 3. And our other fraction will have had a denominator of 4 minus x. Now I don't know what the numerators are, so let's say a and b. They're constants, which we are going to find. And I don't know if it's going to be add or subtract. It doesn't really matter. I'll put in an add. And if it turns out to be subtract, then all that will happen is that b will turn out to be a negative value. It doesn't really matter. Now, because this is not an equation, because the left-hand side and the right-hand side are equivalent, I will, to be mathematically precise, put in an identity symbol, an equivalence symbol. So let's think about what would happen next to the right-hand side. We could combine the two fractions on the right-hand side as a single fraction. So thinking about our common denominator idea, cross-multiplying here, we'd get a bracket 4 minus x plus b bracket x plus 3 all over the common denominator of x plus 3, 4 minus x. Now, because these are equivalent fractions, because the left-hand side is the final simplification of the right-hand side, and because the denominators are the same, the numerators must be equal. Now, if the numerators are equal, this tells us that 2 plus x on the left-hand side must be equivalent to a bracket 4 take away x plus b bracket x plus 3. And our mission is to find the values of a and b. Now, there are two different methods we can use to find the values of a and b. We're going to look at both of them one after the other. So method 1 involves looking at our identity here and then thinking, because it's an identity, because the left-hand side and the right-hand side are identically equivalent for any value of x, we can choose any value of x to substitute into both sides and they will still remain identically equal. That's the whole purpose of an identity, what separates it apart from an equation, for instance. So if I choose very carefully, I can select values of x that will allow me to simplify this very easily. So I'm going to choose, first of all, the value x equals 4, and I'm going to substitute it into both sides. Now, if I choose x equals 4, on the left-hand side, I've got 2 plus x, which is equal to 6. Now, on the right-hand side, see what happens when x is equal to 4. Can you see this bracket here becomes 0, which means a is being multiplied by 0, and so a vanishes out of the picture, which instantly simplifies what we've got to do. X equals 4 substituted into the other bracket gives us 7b. This then allows us to calculate the value of b as 6/7. Now, what value of x should we choose to substitute in this time? It would really help us if we could make this bracket equal to 0, because this then eliminates b from the whole calculation. So yes, we're going to choose x equals -3. Now, substituting into the left-hand side of the inequality, 2 plus x gives us -1. On the right-hand side, we have 4 minus -3, which is 7, so we have 7a, and of course the other part of this disappears. This then allows us to calculate the value of a as -1/7. Now this is brilliant. We've worked out the values of a and b, which means we can revisit the original question, which was, look at this single algebraic fraction, 2 plus x over x plus 3, 4 minus x, and decompose it into a pair of single fractions. Now we know what those single fractions are. Now, the values of a and b have worked out to be fractional, but we would not write our answer out like this. So where I've got a, write -1/7 over x plus 3, plus b, which is 6/7 over 4 minus x. That really doesn't look particularly nice at all. Instead, we're going to bring the denominators of those fractions for a and b into the overall denominator. So this will become -1 over 7 bracket x plus 3 plus 6 over 7 bracket 4 minus x. And there's absolutely no need to expand those denominators unless told otherwise. Now, what have we done? We have decomposed this fraction here, this original algebraic fraction, into its constituent partial fractions. And we have done this via method 1, which allowed us to choose a value of x and substitute it into the identity. So we're now going to have a look at a second method which will allow us to find the values of a and b. Now, this method involves doing something called comparing coefficients, and you have actually seen this before in GCSE Maths when you studied identities. let's look at a very, very simple example. If you're told that x plus 2 is identically equivalent to x plus p, well, the only way this can work is if p is equal to 2, because both sides of the identity have to be exactly the same. One side can be a slightly different rearrangement, but they have to mean exactly the same thing. So in a more complex example, let's suppose we had something like 5x minus 2 is identically equivalent to ax plus b. Now, the only way this can work is if you compare the coefficients and make sure they're equal. So because you have a 5x here and an ax there, the only way that this identity can be true is if a is equal to 5. And because you have a constant here which is negative 2 and a constant here which is b, b has got to equal negative 2. And we're going to use a similar process to find the values of a and b. Now, for simplicity, although some of you may not need to do this, I'm going to expand these brackets here. So I've got 4a minus ax, and then I've got bx plus 3b. Now, if we look at the coefficients of x, first of all, we've got 1x on the left-hand side. On the right-hand side, we've got negative ax and we've got a bx. And in theory, I could write those as a single term, which would be minus a plus b lots of x. So if I start comparing the coefficients, and I start by comparing the coefficients of x, on the left-hand side, I've got 1x, and on the right-hand side, I've got minus a plus b lots of x. And that minus a plus b has got to equal a value of 1, so that we have the same number of x's on both sides, i.e. the same coefficient of x. Now, separately, if we look at the constant term, on the left-hand side we've got a 2, and on the right-hand side we've got 4a, which is a constant, there's no x as a part of that, and we've got 3b as a constant as well. And what have we created? We have created a pair of simultaneous equations. So how am I going to solve these simultaneous equations? Any method I choose to use. So what I'm going to do is rearrange equation 1 so that it neatly tells me that a is equal to b minus 1, and I'm going to substitute that into equation 2, which tells me I've got 2 equals 4 lots of a, or b minus 1, plus 3b. And we simply solve this, so that's 7b minus 4. So 7b is equal to 6, and b is equal to 6/7. And because a is equal to b take away 1, this allows me to calculate my value of a, which is equal to negative 1/7. And we've got the same values of a and b as we had previously. Now, if I were doing the question this way, I would still continue to then write out my pair of partial fractions, but I'm not going to repeat that particular part because we've already done it. So this is another approach to solving the problem and finding the values of a and b, and the approach that we have used here is called comparing coefficients. Some of you may be thinking, well, this is a lot more complex than the previous method, but it still does get you to the correct answer at the end, and there may be instances where it's preferable to use this approach. There may also be situations where actually a combination of both methods works very nicely to get you to the final answer very efficiently. So let's take a look at a second example. We are going to write the fraction 3 over 1 minus x squared in terms of its partial fraction. So we're going to decompose it into its partial fractions. So first job, I'm going to rewrite the denominator in its factorised form, 1 minus x, 1 plus x. And then I'm going to set up the partial fractions currently as a over 1 minus x plus b over 1 plus x. So keeping everything as general as possible. Now, we can write out the right-hand side with the common denominator, or we can go straight to the next step. We know that we're going to multiply this up here. We know that we're going to multiply this term up here. So we know that this is ultimately going to give us a pair of identical numerators. So on the left-hand side, we have 3, and on the right-hand side, we have a multiplied by 1 plus x, and we have b multiplied by 1 minus x. Now, if you're not comfortable with that, put in this step here where you have a multiplied by 1 plus x plus b multiplied by 1 minus x over a common denominator of 1 minus x, 1 plus x. And because that's equivalent to 3 over 1 minus x, 1 plus x, this then gives you my next line of working over here where the numerators are equal. So optional to include this step here. However, now we're at this step, we now need to find our values of a and b. So I'm going to look at both methods again. So method 1, if you remember, was to choose a value of x and substitute it in. So very simply, I'm going to start off by choosing x equals 1. Now, the left-hand side of this identity here is independent of x, which means that regardless of what value of x I choose, it's always going to be 3. Now, on the right-hand side, if I substitute in x equals 1, well, you can hopefully see that this bracket here will become 0, so that wipes out b, and then in the other bracket we will get 2 and then a. So this allows me to work out straight away a is equal to 3 over 2. So let's now choose our other value of x to substitute in. Have you worked out what it is? It's something that's going to allow this bracket to become 0, which is going to be negative 1. Now, if I substitute in negative 1, the left-hand side, remember, will remain as 3. The right-hand side, well, the bracket next to a is going to vanish, but the other bracket is going to become 2b. So straight away, this gives us our value of b as being equal to 3 over 2 as well. So both a and b are equal to 3 over 2. And this then allows us to set up our partial fraction decomposition. So 3 over 1 minus x squared is equivalent to a, remember, over 1 minus x. But of course, I'm going to write the 3 from the a in the numerator and the 2, the over 2 part, in the denominator, like that, for a bit of clarity. And then, of course, my b value, I'll do the same here. I've got plus 3 over 2, 1 plus x. And we have done that. There is our partial fraction decomposition. Now, it's worth noting, we don't necessarily have to substitute in values which make the bracket 0. What if we chose different values to substitute in? Well, you can see for yourself what would happen. Let's imagine we chose to substitute in x equals 2. Now, the left-hand side would, of course, stay at 3, but in the right-hand side, neither a nor b would be removed. They'd both stay there. So x equals 2 then gives us 3 equals 3a minus b. So we end up with a single equation that contains a and b. Well, how are we going to deal with this? We'd have to substitute another value of x in and potentially end up with another equation with a and b in it, depending on our choice. So we'd have to end up solving simultaneous equations. So there's not a huge amount of value in choosing x equals 2 here. We choose a number that deliberately will make one bracket equal to 0. So choose your values of x very carefully if you're using method 1. Now let's look at method 2 again, which, if you remember, involves us comparing coefficients. Now, if we compare coefficients of x first of all, well, on the left-hand side we have 0x. So the left-hand side gives us a 0. Now on the right-hand side, I'm not going to expand the brackets this time. Hopefully you can see just by thinking about it that we'd end up with a lots of x and then minus b lots of x. Now, if we look at the constant term on both sides, on the left-hand side we have a 3. And on the right-hand side, what constants do we get? Well, here we'll get an a, and here we'll get a b. So we end up with a very simple pair of simultaneous equations to solve. Let's add these together. So if I call that equation 1 and equation 2 for clarity, we are adding together equation 1 and 2, which gives us 3 equals 2a. Therefore, a is equal to 3 over 2, and equation 1 clearly tells us that a is equal to b, so b is also equal to 3 over 2, and we get the same answers. So you may find, as in this situation, that comparing coefficients can be just as quick as, if not quicker, than the first method of substitution. Ultimately, find a method that you feel comfortable with, that works for you accurately, and be flexible. Be prepared to remember that sometimes one method may work better than another method. So let's look at a third example. This time we have 3 factors in the denominator. So as we think about our decomposition, we're going to need 3 fractions: a over x plus 2, plus b over x minus 5, plus c over 2x plus 1. Now, the next step would be to ensure that all 3 of these fractions have the same common denominator, which will be the same denominator as the original fraction on the left-hand side. So the most efficient way of dealing with this is to look at the left-hand side, look at what's already there, and look at what each fraction already has in its denominator. So the first fraction already has an x plus 2. It doesn't have an x minus 5, and it doesn't have a 2x plus 1, which means the numerator would also have to gain an x minus 5 and a 2x plus 1. Second fraction already has an x minus 5, but it doesn't have the x plus 2 or the 2x plus 1. So we're going to need to multiply by x plus 2 and 2x plus 1, and here as well, x plus 2 and 2x plus 1. And the third fraction, c over 2x plus 1, well, it already has the 2x plus 1, but it's going to need the x minus 5 and the x plus 2, so we're going to need to multiply by x minus 5, x plus 2, and x minus 5, x plus 2. There's a lot to think about here. Now, again, we could write out all 3 fractions with their new common denominators. We could set up the single fraction with the single common denominator, but ultimately, hopefully by now, with 2 examples under our belt, we know where this is heading. We know that the numerators will form an identity, and the numerator on the left-hand side is going to be 2x plus 3, and the numerators on the right-hand side will be a bracket x minus 5 2x plus 1 plus b x plus 2 2x plus 1 plus c x minus 5 x plus 2. And we have our identity here that we're going to keep referring back to as we continue the question. So our job now is to find the value of A, find the value of B, and find the value of C. And they will always be unique in these questions. You're not going to get multiple possible values of A, B, or C here. So method 1, we need to choose sensible values to substitute in and then go from there. So I'm going to choose to substitute in the value of x equals 5. So on the left-hand side, that's going to give me 2 times 5 plus 3, which is 13. And on the right-hand side, well, x equals 5 will cause this to become 0, so I can forget about a. And I'll also be able to forget about c as well. So I only need to really substitute x equals 5 into the b part here in the middle. And that gives me a value of 77b. So I get a slightly unpleasant looking value of b of 13 over 77. So what next? We're going to substitute in the value of x equals negative 2. So on the left-hand side, x equals negative 2 gives us negative 1. On the right-hand side, well, this is going to vanish and this is going to vanish. So I only need to focus on the a term, and this gives me 21a. So I get another slightly unpleasant looking fraction of a equals negative 1 over 21. So the last one. Well, I'm going to choose something that will make this bracket here and this bracket here equal to 0, which is x equals negative 1/2. So substituting in x equals negative 1/2 gives me 2 on the left-hand side, and on the right-hand side I end up with negative 33c over 4, which gives me c is equal to negative 8 over 33. I can then go back to the original question and feed this into my values of a, b and c. So that gives me a final answer of negative 1 over 21 bracket x plus 2. That's my a part, plus 13 over 77 x minus 5. That's my b part, minus 8 over 33 2x plus 1, that's my c part, and here is my partial fraction decomposition. So now let's take a quick look at the second method, comparing coefficients. Now, on the right-hand side, when you expand the brackets, each of these terms will feature an x squared term, as well as an x term and a constant term. So as we compare coefficients, we need to compare coefficients of the x squared term, then of the x term, and then of the constant on each side. So comparing coefficients, x squared first of all. On the left-hand side, we have 0x squared. On the right-hand side, you're going to have to either expand the brackets or think about what happens when you expand the brackets and then multiply by the a in front of them. But the first yellow pair of brackets would give us 2x squared. So that would give us a 2a as our coefficient of x squared. This pair of brackets here would give us a 2b x squared. So that's 2b as the coefficient. And this pair of brackets would simply give us cx squared, so we'd have a plus c at the end there. So the simultaneous equations that we're heading for are a bit more complex here, and we're going to end up with 3 simultaneous equations that involve a, b and c. You may want to pause here and see if you get the same for when you compare coefficients of x and of the constant term as well. So let's see if we've got the same. If we compare coefficients of x, we have 2x on the left-hand side, and we will end up with negative 9a here, plus 5b here, and then subtract 3c over there, and then the constant term is usually very easy to work out. We've got 3 on the left-hand side. On the right-hand side, we've got minus 5a plus 2b and minus 10c at the end there. Now, I'm not going to work through solving these simultaneous equations at the moment. You can do if you want to. There is quite a bit of algebra involved. Essentially, you're going to have to use one equation, substitute it into both of the others to eliminate a variable, then solve and then keep solving until you find each of the coefficients. The answers will not be that pleasant. As you know, the values of a, b and c in this question aren't that pleasant. What you may also wish to do at this point is experiment with solving these using your graphical calculator. Now, in case anybody needs a reminder of how to do that, you need to select option A, which is the equation solver mode from the main menu. And then from there, you want F1, which is simultaneous. Once you've done that, you need to choose 3 unknowns in this case. And then you need to input in your coefficients of A, B and C, although there'll be coefficients of X, Y and Z in the setup here, and then select F1, solve, and see if you get the correct answer at the end. So you can see some screenshots here of how to enter in the coefficients of A, B and C to work out the values of A, B and C, and the answers here you obviously have to use the FD button to ensure that you can see the answers in their exact form. So we're now going to have a look at a different sort of example. What happens if there is a repeated factor in the denominator of your fraction? So for instance, if I pick as my example 2x plus 1 over x minus 1 squared, x plus 1, how do I deal with the fact that there is a repeated factor in the denominator? Now, let's stop and think about some of the answers I've seen to this question previously. Some people will try and say, well, let's do a over x minus 1 plus b over x minus 1 plus c over x plus 1. Now, this isn't correct because if you were looking for the lowest common denominator, well, the lowest common denominator here of these 3 fractions would simply be x minus 1, x plus 1. It would not be x minus 1 all squared, so that can't be correct. So let's have a look at another answer that I've seen here. So another answer that I've seen commonly would say, well, let's do a over x minus 1 squared plus b over x plus 1, because this gives you a common denominator of x minus 1 all squared, x plus 1. However, this is also not completely correct, so there has to be something else. Now, the actual answer, and we're going to think about why in a minute, is this. When you have a repeated factor in the denominator, yes, you want an a over x minus 1 all squared, and yes, you want a term, we'll have c this time, over x plus 1, but you have to account for the fact that there could have been a fraction like this with an x minus 1 in the denominator on its own, because the lowest common denominator here is going to be x minus 1 squared, x plus 1, and all 3 of these are factors of this lowest common denominator. We're going to illustrate this in a little bit more detail before we come back to this example. So to truly understand this, we really need to go back to adding fractions together. So supposing I asked you to add together the fraction 2 over x plus 1 all squared and 1 over x minus 3. Let's add these together and see what happens. So common denominator, cross multiply. This gives us 2 bracket x minus 3 plus x plus 1 all squared all over a common denominator of x plus 1 squared x minus 3. I'm not going to show the full level of working here, but I will tell you that this simplifies to give us x squared plus 4x minus 5 all over x plus 1 squared x minus 3. So it is possible that a single fraction like this where there's a repeated factor in the denominator, could have been composed of two single fractions like this. However, let's consider a different situation. This time we're going to add together 2 over x plus 1 all squared, 3 over x plus 1, and 1 over x minus 3. We're going to add 3 fractions together. So let's think about the common denominator here. The common denominator is going to be x plus 1 squared x minus 3. That's the lowest common denominator that is divisible by all 3 of the original denominators. So what does each one of these need in its numerator? Well, this one needs an x minus 3. So we'll end up with 2x minus 3 from the first fraction. This one here needs to be multiplied by an x plus 1 and an x minus 3. So we'll end up with 3 lots of x plus 1 and x minus 3. And the last one needs to be multiplied by x plus 1 squared. So we'll end up with plus x plus 1 all squared. And again, I'm not going to fill in all of the algebraic working here, but you end up with an answer of 4x squared minus 2x minus 14 all over x plus 1 squared x minus 3. Now, the wider point that I want to make here is that in both cases we have a fraction which has a repeated factor, x plus 1 all squared, in the denominator. And in this second case, the decomposition involves 3 separate fractions. One where there's a denominator of x plus 1 all squared, and another where there is a denominator of x plus 1. So it's not enough to, when you're decomposing, and then there is a repeated factor in the denominator, to assume that this came from 2 single fractions. There could have been a third fraction with, in this case, x plus 1 in the denominator. So in both cases, the denominator is x plus 1 all squared multiplied by x minus 3. But we've seen 2 different ways in which this denominator could be created. One, where we simply add 2 fractions together, and a second where we add 3 fractions together. Now, the problem with the first example, the first method we used here, is that it doesn't account for the possibility of that third fraction, which the second method accounts for. So we don't do this, we do this second method here. Now, it might be the case that b, the value of b, ends up being equal to 0. That's perfectly feasible, but unless we include it as part of our decomposition, we will not know. So we're going to revisit the example that we started looking at. 2x plus 1 over x minus 1 all squared x plus 1. We are going to split it up into its partial fractions, general to begin with. So a over x minus 1 all squared plus b over x minus 1 plus c over x plus 1. It doesn't matter which letter goes with which denominator. Ultimately, they're just constants at the end. But what is essential is that we must include both of these. So where do we go from here? Well, we need to get to the stage where we have an identity. So we know the numerator on the left hand is going to be 2x plus 1. Now on the right hand side, we just have to figure out what each denominator would need to become the common denominator of x minus 1 all squared x plus 1 and apply that to the numerator as well. So x minus 1 all squared would need to be multiplied by x plus 1. So a would need to be multiplied by x plus 1. Now, in the second part, x minus 1 would need to be multiplied by an x minus 1 and x plus 1. So b would be multiplied by both of those. And in my third part here, c over x plus 1, this would need to be multiplied by x minus 1 all squared, so would the numerator. So this gives me my right-hand side with numerators as well. Let's fill these in. So b multiplied by x plus 1 and x minus 1, and c multiplied by x minus 1 all squared. So here's my identity. So we need to find the values of a, b and c. So I'm going to choose values to sub in for x. So it makes perfect sense for me to choose the value of x equals 1 first of all, because that will wipe out here and it will also wipe out here. So I lose b and c instantly when x is equal to 1. So x equals 1, the left-hand side gives me a value of 3, and on the right-hand side I get 2a, so I can work out that a is equal to 3 over 2 straight away. It next makes sense to work out what happens if x equals negative 1, so that means this will vanish, and of course this will vanish as well, which will leave me with just the c term. So if x equals negative 1 on the left-hand side, that gives me negative 1, and on the right-hand side, that's going to give me 4c. So c is equal to negative a quarter. What next? So there isn't another obvious value of x to substitute in, because there isn't another bracket on its own that I can make equal to 0. So at this point, we just choose any sensible value of x to substitute in. Now, what would be an easy value of x? Well, I would choose x equals 0. That's usually the easiest value to pick. So on the left-hand side of the identity, 2x plus 1, x equals 0, that gives me 1. And then on the right-hand side, remember x is equal to 0. You're substituting that into each of these parts. I'll do it in different colours. Well, x plus 1 is 1, so I end up with an a for the blue part there. Now for the green part, x equals 0 will give me 1 multiplied by negative 1, so negative b. And then for the red part, x equals 0 will give me a simple plus c at the end there. Now, because I know my values of a and c, this then allows me to work out my value of b. So 1 is equal to 3 over 2 minus b minus a quarter for my value of c. I can then rearrange this and work out that b is equal to 1 quarter. I now have my three values a, b and c, which I can substitute in to give me my partial fraction decomposition. So I have 3 over 2 bracket x minus 1 all squared, add 1 over x minus 1, so b was not equal to 0, so that we needed it there to get that central term, and then c was equal to negative a quarter, so that gives me 1 over x plus 1 at the end. And here is my final answer, my partial fraction decomposition. Now, an alternative method, having worked out that a equals 3 over 2 and c equals negative a quarter, we could at this point, having used the substitution method, we could compare coefficients here and choose a simple coefficient to compare. I'm going to look at the coefficients of x squared on both sides. Now, on the left-hand side, well, we've got no x squareds, so we have 0 x squareds. Now, on the right-hand side, we get no x squareds from this part here. From this part here, we'll get 1 lot of x squared, or 1b lot of x squareds. And here, when we expand again, we'll get c lots of x squared, which then tells us that b is equal to negative c. And as we've already worked out that c is negative a quarter, that gives us b equals 1 quarter. So hopefully you can see it can be very useful to use a combination of the two techniques when you're finding your values of a, b and c. So a last note on this, if the original fraction contains a repeated factor in the denominator, don't forget to account for this in the partial fraction decomposition. So let's have a look at a few exam-style questions which require us to perhaps think a little bit more about each example. So we're going to start off by looking at how we link the binomial expansion to the concept of partial fractions. So part 1, nice and simple now, we need to express x over 1 plus x, 1 minus 2x in partial fractions. So that means we're going to express it as a over 1 plus x plus b over 1 minus 2x. So think about the cross multiplication that would then have to take place. This would give us numerators which are identically equivalent like this. And then we're going to sub in key values of x. So I'm going to choose x equals -1 first of all. On the left-hand side, this gives me -1. And on the right-hand side, the b part cancels, disappears, vanishes, is equal to 0. And the yellow part, the a part, gives me 3a. So my value of a is -1/3. I'm then going to choose x is equal to 1/2, which of course on the left-hand side gives me 1/2. On the right-hand side, the yellow part disappears and I'm left with 3/2b. So b is equal to 1/3. And this means we can rewrite these as -1 over 1 plus x with the 3 in the denominator, and then plus 1 over 3, 1 minus 2x, 3 in the denominator again. So, part 2. We've now got to use binomial expansions to show that this, which is our original algebraic fraction, can be written in this format here, where a and b are, lowercase a and b are constants to be determined. So, having written our original fraction as a pair of partial fractions, we're now going to rewrite each of these in this format. So rather than factors in the denominator, we're going to set them up in the numerator with negative powers. And we now need to perform a binomial expansion, which means we need to recall our formula for the binomial expansion, which will be given to us in our exam formula booklet. Now, just in case we don't have it to hand, I've written it up in red on the top right as far as the x squared term. We don't need to go further than that in the result that we are finding, so we'll leave it at that. Now, in both examples, the value of n is equal to -1, but in each we have a slightly different value of x essentially to be substituted in. The first one's nice and easy, it's just an x, but in the second one we're replacing x in the formula with -2x. So here we go. So I'm not going to continue writing the equivalent symbol in this for the moment, we'll leave that, because ultimately it's going to be approximately anyway, as we're not using all of the full expansion, we're stopping at the x squared term. So this is -1/3 of 1 plus nx, so that's -1 multiplied by x, plus n minus 1, x squared, over 2 factorial, plus ... And then the second part, and then we've got 1 plus n multiplied by x, which this time is -2x, plus n minus 1 multiplied by x, again, which is -2x all squared, all over 2 factorial. Close the second bracket. And then we've got to simplify and collect our like terms. Now let's expand and simplify. So we're going to get -1/3 plus 1/3 x minus 1/3 x squared from the first part here. And then we're going to get from the second part a third plus 2/3 x plus 4x squared over 3. Remember, we're only going up to the term in x squared, so in theory we probably should put an approximately symbol here. Now, when we look to simplify, we have a negative a third here, which cancels with the negative a third here, which is good because we're only expecting terms in x and x squared at the end. We have a third of x plus 2/3 of x, so that gives us a single x term. And then last of all, we have negative a third of x squared plus 4/3 of x squared, which simply gives us plus x squared. So at the end of all this, we need to state the values of a and b. It does say a and b are constants to be determined, which means state a and b. And we can see from what we've done that a equals b equals 1. Now, in terms of the validity conditions, that's the last part of this, linking back to the binomial work we've done recently, state the set of values of x for which the expansion is valid. So let's look at each part of this now. From here, we can see that this part is going to be, this expansion here is going to be valid for mod x less than 1. And this part over here is going to give us mod 2x less than 1, or mod x is less than a half. Remember, we've talked about this in the previous topic on the binomial expansion. When we have got multiple validity conditions, we always take the stricter of the two, and the stricter of the two is this one. So the set of values for which the expansion is valid is mod x is less than a half, or negative a half is less than x is less than a half. So we're going to look at one last example. You may want to work this through yourself and then come back and check the answer, or follow it through together with the video. So part 1, we have been given the partial fraction decomposition format. We now need to find the values of a, b and c, showing that a actually in this case works out to be 0. So this is slightly different to the example we did previously, where there's a repeated factor in the denominator. We're then moving on to a binomial expansion, and then a combined binomial expansion at the very end. So first step of this is to look at our numerators on the right hand side of these fractions. I'm going to use the existing notation that's been left here for me. So this one needs to gain a 1 plus x and a 1 minus 4x. So the numerator also needs to gain a 1 plus x and a 1 minus 4x. So we have the correct denominator. The middle term needs to gain just a 1 minus 4x. So the numerator will also gain a 1 minus 4x. And the last term here needs to gain a 1 plus x all squared, so the same in the numerator. So we know that we will end up with equivalent numerators at the end of this, so this will give us 3 plus 2x squared is equivalent to a multiplied by 1 plus x, 1 minus 4x, plus b multiplied by 1 minus 4x, plus c multiplied by 1 plus x all squared. So choosing our values very carefully, let's choose x equals negative 1 first of all, which gives us 5 on the left hand side. And on the right hand side, both a and c will disappear from this for the moment. We'll eliminate both of them. And the central term will become 5b. So b very simply equals 1. We'll then choose x is equal to a quarter. So on the left hand side, we get 25 over 8, and on the right hand side we're going to wipe out a and b, and this leaves us with 25 over 16c. So from here we can see that c will work out to be equal to 2. And we're in the same position as previously. we're going to either need to check coefficients, compare coefficients, or sub in another value to work out what a is. I'm going to choose x equals 0. So on the left-hand side, this will give me 3. Now remember, on the right-hand side, this isn't going to wipe out anything just yet. So the first part, if x is equal to 0, gives me a single a. The second part gives me plus b. And the third part gives me plus c. Remember, I'm substituting x equals 0 into every term. So 3 equals a plus b plus c, but of course, remember, c is equal to 2 and b is equal to 1. So this therefore gives me a equals 0, which is what we were required to show. Now, we weren't actually officially asked to write out the three partial fractions. We were just asked to find the values of b and c and show that a equals 0. But just to finish this off, we now know that this term here no longer is required because a equals 0. The central term becomes 1 over 1 plus x all squared, and then the last term becomes 2 over 1 minus 4x. And this is our partial fraction decomposition. Now, part 2, we need to find the first three terms of the binomial expansions of 1 plus x to the negative 2 and 1 minus 4x to the negative 1. So to refresh our memories, the binomial expansion is up at the top there. So starting with 1 plus x to the negative 2, so we can see that n is equal to negative 2 here. And x is just x. We have the 1 at the beginning, so we are good to go. So we've got 1 plus negative 2 multiplied by x plus negative 2, which is n, multiplied by n minus 1, which is negative 3, multiplied by x squared all over 2 factorial. Now we're only doing the first three terms, so this simplifies to give us 1 minus 2x plus 3x squared. Now let's look at the other expansion that we've got to do, which is 1 minus 4x to the negative 1. This time n is equal to negative 1, and we've got negative 4x to replace x in each part of the expansion. We have the 1 at the beginning as needed. Here we go. So we've got 1 plus n multiplied by x, which is negative 4x, plus n minus 1, which is negative 2, multiplied by negative 4x all squared, all over 2 factorial. And then let's simplify. So this gives me 1 plus 4x plus 16x squared. Because again, remember, we're just tailing off after the first three terms. In theory, we probably should say these are approximately rather than actually equal to completely. So the last part of this asks us to say whether we can find the first three terms in the expansion of this. Okay, so this of course is our original partial fraction, which is 3 plus 2x squared over 1 plus x all squared, 1 minus 4x, which we wrote as a pair of partial fractions, 1 over 1 plus x squared plus 2 over 1 minus 4x. So we're now going to rewrite these as 1 plus x to the negative 2 plus 2 bracket 1 minus 4x to the negative 1. And of course, we can now bring in these here and here. So we can say this is approximately 1 minus 2x plus 3x squared plus, and we need to make sure we've got two lots of the second part, 1 plus 4x plus 16x squared. And then we simply simplify this, so that gives us 3 plus 6x plus 35x squared. So we have the first three terms in this expansion.